All right, young scholars, today we are going to cover the topic of recursion. The idea behind recursion is that it's a way of making a function call itself, which often allows us to make hard problems much simpler. In essence, it reuses the code over and over to produce a result. On Thursday, you'll see the common examples of how to use recursion, such as the Hanoi problem, etc., factorial problems, many of which will be mentioned in the lecture today. So almost always used in advanced mathematical problems is recursion, because as mentioned, it makes harder problems easier. So one common example is a factorial. The mathematical notation for a factorial is whatever your number is equals n times n minus 1. So if you have a factorial of 0, it equals 1. You'd have factorial n equals n times factorial n minus 1, as long as it's greater than 0. So in this example, what would the factorial of 4 be?
It's 4 times 3 times 2 times 1.
Yep. So what is it?
4 times 3 is 12. 4 times 3 times 2 is 24. Times 1 is 24.
Yep. And as you see in the remaining slides, factorial of 4 is 4 times 3, 4 times 3 times 2, 4 times 3 times 2 times 1, etc. So as we go through our factorial, we should end up with a final solution of 24. So again, 4 times 3 times 2 times 1. When you put that in terms of coding, it's just factorial 4 which would return 4 times factorial of 3, which that returns 3 times factorial of 2. The factorial of 2 returns 2 times 1. And so on and so forth. So in your head, obviously you go through that code and it's fairly simple. With programming, it's a little different. It requires recursive programming. We're using that same factorial in 4 different steps. If it was a factorial of 3, it'd be 3 steps, all doing the same solution over and over again. So 4 times for factorial of 4. It's basically running that factorial 4 times in order to give us the answer that we need. So each step will provide a different return. Once you're complete, it's going to return that 24 that we showed before is our answer, the factorial of 4. 4 times 3 times 2 times 1. So that one line of code, factorial 4, had 9 steps associated with it. That's what recursion helps us with. Instead of writing 9 lines of code, we just call on that factorial 4 different times. It runs through the program, ultimately returns our solution of 24. So here is those 9 steps and basically a stack, which we'll talk about later in the semester. It builds upon each of the parts. So to compute factorial 4, we need to have factorial 3. To compute factorial 3, we need to have the factorial of 2. To complete the factorial of 2, we need to know the factorial of 1. To know the factorial of 1, we need the factorial of 0. So that goes through all of those 5 steps and then goes backwards. Okay, we have factorial 1. Let's add it in a factorial 2. Okay, we got that. Add it back in to 3. Add it back in to 4. And then it goes backwards to provide the answer of 24, just as we showed with the 9 steps here. It goes forward to get all of our solutions that we need, and then it goes back up the chain to produce our final answer. So another possible example would be a factorial of 0, which is obviously going to give us the answer of 0. But as you noticed, these 9 steps for the factorial of 4, the only return we see is going to be that 24. So there's 9 separate steps that are happening behind the scenes. The steps are not seen visibly by you when you put in factorial of 4. All you would see is the 24, the return of the answer. And that is what recursion helps us with. To basically, as I said, make bigger problems much smaller. Obviously, you don't want to return 9 different answers to a user when they just want the answer of what is the factorial of 4. So if we had the factorial of 5, it would add an additional step to that. It would be 5 times 4 times 3 times 2 times 1. So another commonly used mathematical problem associated with recursion is called the Fibonacci numbers. So the Fibonacci sequence is where each number is the sum of the previous 2 numbers. So here the third number is 1. It's the sum of the previous 2, 0 and 1. So the 2 is the sum of 1 and 1. The 3 is the sum of 1 and 2. The 5 is the sum of 3 and 2. The 8 is the sum of 5 and 3. The 13 is the sum of 8 and 15, and so on and so forth. And like an array, all of these numbers would have indices associated with them. So 0 and 0, 1 and 1, 2 and 1, 3 and 2, 4 and 3, etc. So this line here has cut it off at 11 numbers. However, the Fibonacci numbers or sequence can go on and on as long as you'd specifically like it to. That's why recursion helps us. If you had a Fibonacci sequence of, let's say, 88 numbers, obviously you just prefer to have a few lines of code, which recursion helps us with, instead of, let's say, an entire program. So again, there's a great deal of steps involved. In this specific example, just with 11 numbers for this Fibonacci sequence, there's 17 different steps involved. So again, wouldn't you prefer just one line of code as opposed to writing a full program? Again, that's what recursion would allow us to do. Create, or solve rather, huge mathematical issues using a few lines of code because they're called over and over again. So basically, you're breaking your issues into subproblems and then reassembling. Who's had a discrete math class?
I
Nobody?
have.
So
Okay.
Amelia, in discrete math, you've learned about proofs, right?
Yep. You learn about proofs in geometry as well.
Okay. Now, what do you have to do with the proofs?
What do you mean?
Don't you have to write out all of your steps?
Yeah, of course.
So recursion allows us to do the opposite. We know all our steps here in the background. We see, okay, there's going to be 17 steps if we try the Fibonacci sequence for 4. But with recursion, we might just have one line of code, 2 lines of code, 3 lines of code, 4 lines of code, as opposed to writing out every individual step. You see, just returning a Fibonacci sequence with 4 numbers requires 17 different steps. Recursion allows it to where the overwhelming majority of those steps are happening behind the scenes. You don't need to put more code in to do it. If somebody's not familiar with Java programming, they don't even know that these 17 steps are happening behind the scenes. All they see is those couple lines of code and the result. Whereas in discrete math or geometry, when you're doing a proof, you might write out 10 different steps that solve your problem. Whereas recursion, it might just say step 10 and then your solution. Whereas when you wrote it out, all those 10 steps, they're seen behind the scenes. The Java program, okay, this is recursion. We're doing a Fibonacci sequence. We'll do all these steps. The user may not necessarily care that all of those steps are being completed. They just want an answer. What's my answer? Okay. So with a Fibonacci sequence with 4 numbers, what would it be? 3, right? We start with 0, then 1, then 1, then 2. Our 2 and our 1 is 3. So all recursive methods have the same characteristics. The method is implemented using a conditional statement that leads to different cases. One or more base cases are used to stop recursion. Every recursive call reduces the original problem, bringing it increasingly closer to a base case. So that's what you saw here. 17 total steps. It might be 3 lines of code. For each of those cases, okay, we have to do this, we have to do that. All right, we're done. So recursion will break those bigger problems into smaller problems. Like I said, you might have a proof in discrete math where you have to list out 10 steps and then your solution. Whereas recursion, it might break it into, let's say, 3 steps and then your solution. Ideally, you just want to make it 1 step, but it depends on what your problem is, on how many steps you could break it down to. So in this example, we're creating a recursive problem that is going to allow us to print any number of welcomes. So whatever we put in for n will allow us to print out that number of messages. So rather than print line multiple messages on multiple lines, we can set it up to where we can print multiple messages at the same time. Now, obviously, this may not necessarily be something you want to do, but you might have an instance where you might want to welcome 8 different people to class, for example. You would set up this n print line welcome, and maybe the n serves as an individual message for each person. So, welcome, Grace. Hello, Amelia. Happy birthday, Calvin. Whatever it may be. So the base case is going to be 0. Once your n gets to 1, it'll be 1 minus 1, and it will be equal to that 0. Which means that it will keep printing messages until it hits that 0. So if you were to set n to be 8, how many messages would it put out? If it stops at 8 or it stops at 0 and we have 8 messages, how many messages will it display?
Seven? N
Yep.
minus 1?
N minus 1. So it's going to display 7 messages. Then it hits the 0 and stops. Because that next time when it tries to put out an 8th message, it's at the base case. It stops. So if you had it as 6, it would be 5. If you have it as 18, it would be 17. Obviously, as I mentioned, it's more common with solving mathematical problems than posting a bunch of different messages. But as I mentioned, in this way, instead of just having 18 lines of code, print line, whatever your message is, you would have it set up recursively to do them all at once. So there are also what are called helper methods within recursion. So sometimes you might find a solution by defining a recursive method to a problem that's similar to the original problem you had. So the original method can be solved by invoking the recursive helper method. So you might have some kind of code within your class that allows you to solve a problem even quicker, which is called a helper method. So if we've seen in the past, usually our methods allow us to call something, to do something. Where we had, especially with our abstract classes and interfaces, we had like a void noise, and the cat meowed and the dog barked. Recursion helper methods are in essence the same idea. They're going to help break down the problem even further. So here's an example. We're creating a recursive method called isPalindrome. All it's doing is creating a new string so then we create a helper method, excuse me, which is this public static Boolean isPalindrome. As long as our length is high and not low, we'll produce a palindrome. Otherwise, we'll look to see how many characters are within our palindrome. So everybody knows what a palindrome is, right? A word that's the same front and back.
And backwards.
Yep. Like race car, for example.
You can have whole phrases. Like I think Abel was I ere I saw Elba isn't a palindrome.
Yep. So what this helper method is now letting us do is in essence check. Hey, we inputted string S and we had race car. Okay, it's a palindrome. All right, return the palindrome. If it's not a palindrome, we double check. Okay, how many characters is it? Initially, all we're doing is just returning the palindrome. We're not even checking to see if it actually is a palindrome. That helper method allows us to establish cases. Okay, is it actually a palindrome? If it's not, okay, we don't worry about it. We're just looking for palindromes. So similarly, we'll focus on this, I think, next week with sorting. You could use recursion for what's called selection sort. So if you wanted to find the smallest number in a list and swap it with the first number, you would ignore the first number and sort the remaining smaller list recursively. So what does that mean? If you had the numbers 1 through 10, and you added in a new number, 0, what happens?
Zero is gonna be swapped with the first number.
Ideally, yep. But with the recursion selection sort, it's going to ignore that first number. Okay, the first number is 1. So the 0 might end up between the 1 and the 2. So often they'll use binary search in recursion instead of selection sort. As you'll see later in the semester, selection sort is often used on its own without recursion in order to give us what we're looking for. So you want the 0 to be before the 1, not between the 1 and the 2. Whereas with binary search, you can create cases. Do you want the number to be in the middle? Do we want it to be equal to the middle? Do we want it to be greater than the middle? Where do we want to put that new number? So you could use different cases. If it's less than the middle number, we'll put it in the first half of the array. If it's greater than the middle number, we'll put it in the second half of the array. If it's equal, we'll put it right next to that number, and our search is done. So in the first case, let's say we had 1, 2, 3 as the numbers of our array. And we wanted to put in the number 4. Okay. It's greater than that middle number of 2. So we put it in the second half of the array. So we would exercise case 3. If we had 1, 2, 3 in our array, and we wanted to put in the number 1, our case number 1 would be executed. It's less than the middle element of 2, so we put it in the first half. If we had an array 1, 2, 3 again, and we wanted to add the number 2, it would exercise case number 2. It's equal to the middle element, so we might put it to the left of it, we might put it to the right of it, but it doesn't matter. We stopped. We don't look at the 3 because we already matched that middle number. So case 3 would look at every specific number in that array. If we want to add the number 4 to an array of 1, 2, 3, case 3 has to look through the entire array. By doing that, in essence, we stop after whatever case solves our issue. So if we wanted to add the number 4, okay, we have to go through case 3 because it's greater than our 1, 2, 3, our 2 being the middle element of the array. But if we just want to put in another 1 in our 1, 2, 3, then we stop at case 1. It's less than the middle element of the 2. So if we had an array 1, 2, 3, 4, 5, which would execute case 3? What number would we have to put in? So if we had an array 1, 2, 3, 4, 5, what's the middle element?
3.
3. So for case 3 to happen, we have to be putting in a new number that's greater than 3. If we're going to execute case 2, the number has to be 3. It's got to be equal to the middle element. If we're going to execute case 1, it has to be any number less than 3, 1 or 2, obviously. So those are pretty basic examples, but obviously the more numbers that are involved within your array, the bigger possibilities you have with your different cases. So the most common recursion problem is called the Tower of Hanoi problem. So in essence, there are n number of disks labeled 1, 2, 3, etc., and 3 towers labeled A, B, and C. So no disk can be on top of a smaller disk at any time. All of the initial disks are placed on towers A. You can only move one disk at a time, and it must be the top disk of the tower. So who has ever seen this problem? You might have seen this if you play like, keep your mind sharp kind of games. Nobody's seen it? So here's how it looks visually. In this example, it's just giving 3 disks. So you'd have the biggest disk at the bottom, a medium-sized disk, and then another disk at the top of it.
Like the baby toy?
Yep. And you have to move the disks to different spaces in order to, in essence, have the same setup you have in A for one of the other possible towers. So initially, you take that smallest piece off the top and put it towards the second tower. Then you take that medium-sized piece and bring it to the third tower. Then you would take that smallest piece from the second tower and place it onto the medium-sized piece on the third tower. Then you would drag that giant piece from the A tower over to the B tower. Then, because you can't move 2 at once, you would have to take that smallest piece and move it from the C tower over to the A tower. Then you would take that medium piece, bring it from the C tower over to the B tower, and then lastly, take that small piece over from the A tower onto the B tower. Obviously, it's very simple to do with only 3 disks, but there may be instances where there's more than 3 disks. So you would have to maneuver these around using multiple different strategies. Now, since you cannot move 2 at once and cannot place a bigger one on top of a smaller one, see how it took 7 different steps? Where we moved smallest here, medium there, then put one on top of each other, flip the biggest one over, move the smallest one to where the biggest one was before, etc., until you now match in Tower B what you had initially in Tower A. So in theory, the more disks you have, the bigger the problem becomes. So your first step is to determine how many discs you have. Then, ideally, you want to move from A to C. Whatever your bigger pieces are. Then, in theory, your biggest piece gets moved from tower A to tower B. Then you would move your smaller pieces from tower C onto tower B over time. As you saw in the previous example, you might have to drag a piece over from C to A in order to properly do that. So here it is written out in essence text. You would move that first disk from A to C in order to clear out tower B. Then you would move your biggest piece from tower A to tower B. Then from C to B with the assistance of tower A, just as you saw in the prior example. The smallest piece was on top of the medium piece on C, but you can't move two at once. So you drag the smaller piece over to A. You take that medium piece from C, drop it in B, and then drop your smallest piece back on top. So as I think it was Grace said, it's basically like the baby toy you have, right? You have the giant blue circular piece. You have the middle-sized yellow one. Then you have the smallest sized red piece. And you move them around to navigate until you replicate that same original position within another tower. So in theory, it doesn't necessarily matter whether you have it in tower B or C, but in theory, as you go through the steps, ideally you want to use that tower C so that you can move over your biggest piece from tower A to tower B to then utilize A and C to complete your reassembly. So another kind of mathematical problem is called fractals. I'm sure you've seen these before in geometry, but you may not necessarily have been specifically told what they're called. But a fractal is a geometrical figure, just like triangles, circles, rectangles, that are divided into parts, each of which is a reduced size copy of the whole. So the most simplest one is called the Sierpinski triangle, named after a famous Polish mathematician. So how many triangles are here? In this example, the second screen here.
It looks like 4.
We have one big triangle with 4 smaller triangles inside of it, right?
Oh, so technically 5.
Yep. How about in this third example? We have the one big triangle around. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 inside. So how many is that total?
14.
14 different totals. Yep. Now, obviously, in this example, we can kind of look at this and see this, but it takes us some time to count those specific numbers. So in this first example, we just have one easy triangle, easy to see. Then we have 3 or 4 triangles within that big triangle. So there's 5 total. And obviously, the more fractals or different images we have, the harder it becomes to count all of them. So when you are recursively drawing them, you could just use display triangles, order -1, P12, P2, P23. You're creating new points. So initially you have one triangle drawn. Then by simply adding this second triangle here with these points, P12, P2, P23, you have now created 4 triangles within that bigger triangle. So in essence, you have created 1, 2, 3 other triangles outside of that new triangle that you've drawn. So have you seen in the past, iteration is in essence that plus plus, minus minus, where you're adding onto something or running something repetitiously using a loop. Recursion is a little different than that. While you're doing the same thing over and over again with iteration using that loop, you're technically doing the same thing with recursion. However, it requires more system usage. So each time the program is calling that method, there has to be space assigned to where it's being used. So in this example, if we're creating one triangle, obviously that doesn't require a lot of system resources. But if we're creating 5 triangles, obviously that requires quite a bit of resources, right? So think of it just like if you had a pencil and paper. Very quick to just draw one triangle, right? If you went ahead and drew one triangle and then drew another triangle in the middle, obviously that takes more time than just doing it once, right? But then if you were to draw 14 different triangles within your one triangle, obviously that takes even more time. So that is what the purpose of recursion is for us. Instead of, in essence, writing 18 lines of code to create all these different triangles, we have, okay, we just draw that second triangle within the triangle. Now we've created 4 different triangles within that one big triangle. When all we did was draw the big triangle and this small one that's lined up with the dots. So that may have been 2 lines of code in order to produce, in essence, 5 triangles using recursion. So the primary advantage, as I mentioned, for using recursion is to solve larger problems, especially mathematically, in a simpler amount of steps. So you saw here with the triangles, instead of drawing 5 separate triangles, we may have just created this one big triangle. Okay, display triangles, order P1, point 1, point 2, point 3. Okay, created that one big triangle. Then we create another triangle. We would have the order P12, P31, P23. Just create that outlined second triangle. And now we have, in essence, 5 total triangles. 2 lines of code, as opposed to if we wanted to create 5 triangles, 5 lines of code. So recursion allows us to break down larger problems into smaller solutions. So like I mentioned, with a geometric or discrete math proof, you might have 10 steps. You look through those 10 steps. Which steps are the most important? Which steps matter most? Maybe only 3 of them matter. That is, in essence, what recursion does for us. Those 3 steps, we actually need them. They matter most, okay? Recursion allows us to break down the problem from those 10 steps that we wrote out into 3 basic steps or examples to go through. So I believe on Thursday, when we go through our specific example code that I have, an example program of the Fibonacci sequence that we're going to go through. And I'm also very certain that I have one of the Tower of Hanoi problem. So we'll see specifically how recursion works within the code. Now, obviously, as you've seen in the past, some of this looks much easier visually when we look at it in this example. When we go through the code, it becomes a little trickier and more advanced. But as I mentioned, the point with recursion is that, in essence, you're breaking down a problem into the smallest amount of steps possible to solve the problem. So think of it like you need to fill your gas tank in order to drive to work today. What's the easiest method to get that issue solved? In theory, the easiest method would be you get ready for work, you leave your house a couple minutes early, you go to a gas station on the way to work and fill up your gas tank, right?
Yeah.
Instead of, okay, I'm going to go out, get some gas, come back home, change, make multiple trips of it, right? In essence, that is what recursion is doing for us. Okay, so since we have some time left over, I want to ask if any of you have given any thought to putting together your group for the project at the end of the semester. So that in the project for this course, you're going to set up a program where you are going to either create a hangman game or a tic-tac-toe game, and then give a presentation of that the last week of class. So you're going to be scored 20 points for the program running effectively, 5 points for making sure that you have comments within the code, demonstrating which of the group members did what section, and then 15 points that last week of class. Each group will give a 20-minute presentation explaining why they chose one or the over the other, how they plan to create the game, how long it took them to create the game, who did what section, provide a demonstration, etc. So if you go into the folder labeled 1128 and 1130, you'll see that I've given you YouTube videos. These are examples on how to do each of those games. You're more than welcome to copy this exactly or create your own version of the tic-tac-toe game and the hangman game. But in essence, they're going to be, obviously this is going to be group work, a group project. So I believe we have 7 students total in the class. So I was thinking maybe we had 2 groups of 2, another group of 3. Have any of you given any thought to who you might want to have as your group members?
Yeah, me and Grace are gonna work together, I think.
Okay. So Amelia and Grace are going to work together as a team. Okay. Does anybody else have any thinking of who they might want to work with? Zaza and Lana, are you in the same group in the other class?
I think Alana is in mobile applications. I'm not sure though.
I know, but are you in that group together in the
Oh,
apps?
I'm with other people that are in that class. I
Okay.
mean, I don't mind working with her if she's okay with that.
Lana, would you like to work with Zaza? Yes, no, maybe so. Franny, do you have a group set up?
Not yet.
No?
I can work with her if she wants.
Okay. Franny and Zaza want to work together? Does that work for you?
I'm fine with that if anything.
Okay. So then we'll do Zaza and Franny. And then who do we have left? Calvin. Lana and Al, right? Okay, so what I'll do on Blackboard is just like I did with the other class. I'm going to create a space for you guys. On Blackboard. Or if you go into the Groups tab, it should allow you to communicate with each other through those specifics. So Zaza and Franny are going to work together. Okay. Amelia and Grace are going to work together. Does this show up? Or are you guys only seeing the PowerPoint?
It's just a
We're
part.
only looking at the PowerPoint right now, yeah.
Okay. So now you can see it?
Yeah,
Okay. So if you go into this group tabs on Blackboard, you'll see that each of these groups are now set up. So group 3 is Lana, Al, Calvin. Group 2, Amelia and Grace. Group 3, Zaza and Franny. You should be able to message back and forth, set up some kind of communication. Start with it this way, and then you're more than welcome to jump into what you guys are more commonly doing these days, like a group chat, whatever it may be. But keep in mind, as I said, there are examples on how to do with it, whichever one you'd like to do, whether it be the hangman game or the tic-tac-toe game within that 1128 and 1130 folder. And in that same folder has the group project, assessment, like how you'll be scored, as I went over. The majority is, does your program work? And does it clearly have comments that, okay, Amelia did this half, Grace did this half. Now, obviously, for the group that has 3 instead of 2, everybody's going to do 33% of the code as opposed to 50% for the other 2 groups. And then that last week, those presentations would occur. So since we have both days set up, you guys are more than welcome to say, okay, we'll do all of them on Tuesday. All 3 will get done. And then probably the 7th, I'll have like an extra credit or something set up for everybody to do in order to hopefully bump up their grade if they need to. So, as I said, that is not going to be due until the later in the semester. So the 4th of December, but as you will notice this week, we're up to homework 8. And there's only 10 homeworks total. So you'll notice that after this week, even though we still have quite a bit of lectures going on, there's only going to be 2 more homework assignments for the programming assignments. So as you're moving forward, as there's less assignments within the course, obviously you're able to spend more time working together on those projects. So again, like I said, look through those videos, determine which one you might want to use over the other. It's entirely up to you. You could use this exact these exact videos and have the program be exactly as they have done them. Or you could look at that and say, oh, okay, I don't necessarily like the way they have it done, so I'm going to do it a little differently. That's entirely up to you. But as I said, you want to think about which one you'd prefer over the other, because that's going to be part of your presentation. So are there any questions on that? Nope.
As of
Go ahead.
I was saying, as of right now, no.
Okay. So I know when a lot of people think of presentations, they think of, using Google Slides or Microsoft PowerPoint. But like I said, when you're presenting this, you don't necessarily need to do that. You're just going to give a 20-minute presentation on why you chose the game. Let's say you chose Hangman over Tic-Tac-Toe. Just tell us why. How you went about planning to create the game. That could be just as simple as, hey, we watched that video and I decided to do this half and my group member decided to do this other half. And it took us, 4 days of working together. And then you're going to walk us through a demonstration of how that worked. So let's say, since it's 20 minutes, you might want to have 10 minutes where you're talking about all those specifics, and then 10 minutes where you're giving a demonstration. Because obviously, it might take a minute or two for it to compile and then run. And then specifically with a Hangman game, it's going to take obviously more time to demonstrate how it works. We have to solve whatever the word is. So we need to be able to provide letters. Whereas tic-tac-toe, that demonstration might be a little shorter. All right, so if there are no questions regarding that, I bid everyone a good afternoon, and I will see you on Thursday, where, as I said, we'll go through examples of recursion programming, where hopefully you guys will be able to effectively solve homework assignment 8, which will be to use recursion to calculate a factorial when a user inputs X and Y. So we'll have a similar example to that on Thursday as well. So if there are no questions, I bid everybody a good afternoon, and I will see you on Thursday.
Bye. All right, bye, Professor. Have a good one.
Take care.